Quizzes will be returned in lab. The key is posted upstairs. The grades range from 10 out of 10 to 0 out of 10. Okay, please make sure you learn from the quiz. Up here, this one was Z. We've done that already. How about number 2? How many chiral carbons does this compound contain? 2. Anybody?
1.
2. Yes, 2. There's one right there. Okay, I can start, or we can do this. And the other one is right there. 2 chiral carbons. What's a chiral carbon? It's a tetrahedral carbon with 4 different things attached. That's it. There's no other tetrahedral carbon with 4 different things attached. 2. There's no stereogenic alkenes, etc. Anytime you see a structure, you can look at it and say, okay, hey, this is an opportunity to maybe test my knowledge on this, or this, or this. 2, how'd we do? 2 chiral carbons. Please do the others. After the day, should be able to do almost most of them. Let's start by looking at 2-butanol. This is where we left off. Enantiomers of 2-butanol. Show the enantiomer of that. Well, there's 2 different ways. We could have a mirror image, and we could show it mirroring. Does that look like it's mirroring? Including the backbone. Just look in the mirror and see that. I think the answer is yes. Okay? First off, what we have here is this RS. Because when you have a chiral carbon, you can have 2 different configurations. Which configuration is this? RS. Oxygen is 1, carbon with another carbon would be 2, carbon with just H is 3. H is in the back here, so that's good. With H in the back, with low priority group in the back, 1, 2, 3, what is this? R. Which comes from the Latin rectus, which means right. That is, the clock is turning to the right. Okay. What is this one over here? Why do you say yes? How do you know it's S?
Because the other one was over.
Oh, it's a mirror image. Do you agree it's a mirror image? Yes. Mirror image is going to be the other. When you go home tonight, hold up your right hand. Look in the mirror. Or not right hand. You can do this. Hold up your right arm. Look in the mirror. Your image is going to be holding up its left arm. When you look in the mirror, everything's reversed. Okay? Yeah, this is S. Okay? I'll bet you a steak dinner it's S. We drew it as a mirror. Okay, if we identify it's 1, carbon with carbon is 2, 3, H is in the back. What is this? 1, 2, 3. What is this? Counterclockwise? That's S, correct? Yeah, it's S. Mirror image. S comes from sinister, which is Latin for left. The clock is turning to the left. Okay. So these are the 2 mirror images. By the way, you could have drawn one of these. Let's see. What if I had drawn it like this? Is this a 3rd way to draw the compound? First off, is that 2-butanol? Forget stereochemistry. Is it 2-butanol? Yeah. Okay. So that is a stereoisomer. It has the same conductivity. Or it's the same, I don't know, but it is the same connectivity. Okay, so, by the way, what do you want to call this compound? We can put R in front of this. Now we have a stereochemical descriptor. What do you want to put in front of this guy? S, 2-butanol. What is that over there? What is that over there? This is S2-butanol? Yes, this is S2-butanol. These are the same thing. How do we know that? Well, butanol, you can determine, you know it's 2-butanol, but let's do RS. Okay, 1, 2, 3, that's priorities. Where's the H? It's back? No, it's forward. 1, 2, 3 is clockwise. But if the low priority group is forward, what do you need to do? Now your book would tell you to turn the compound around. I say, no, don't do that. I say just reverse your finding. 1, 2, 3 is clockwise, that's R. But since the H is coming forward, we turn R to what? We have to switch it to S. This is S. Thus, if that's S and this is S, they're the same thing. These are the same thing. There's two there. They're both S2-butanol. Now, how can we also know that S? Because remember, I've said this before, if you keep the backbone the same, how do you get the enantiomer? Just switch the bold to dashed. See here, over there, the backbone is the same. Zip, zip, zip. If you keep the backbone the same, we just reverse the bold to dashed and we get the enantiomer. But you can confirm that by doing the R and S. Okay? So there's two ways to show the enantiomer, and usually most people will show it this way. They'll just reverse the here. And they usually will not draw the mirror image. These are the same thing. If you take this and turn it around, see the ethyl is coming this way, turn it around, the ethyl will be then going that way. Also, if that's back, the OH is back, if I turn it around, it's now forward. These are the same. Okay. Now we have, these are enantiomers, so they're optically active. That means one will rotate plane polarized light one way, one will rotate PP light the other way. We have some data. Alpha in brackets, that means specific rotation. And when it's in brackets, it means it's been normalized. Okay, and we'll be doing this in lab this week. Polarimetry of naproxen. We'll be working with naproxen sodium generic, which is bought from Walmart. Now, it should be only one enantiomer, because the other enantiomer is toxic to the liver. Is Walmart selling both enantiomers? Or are they selling just one? If they're selling both, they're half of the compound's toxic. We'll test them out. If we find some negative findings, we'll take a trip to Walmart, coming to the manager. It says here, specific rotation for S is 13.5. That's alpha in brackets. Specific rotation equals 13.5. You put degrees here. That's the rotation for S. The R, which in enantiomers rotate equal and opposite directions. So that's 13.5 degrees positive. This is negative 13.5 degrees. Okay? Now there's no negative sign. This is positive. Okay? So this rotates to the right. And this rotates left. It's negative. Okay, if you rotate to the right, you're called D, which stands for dextrorotatory. If you rotate to the left, what do you call it? L, which is called levorotatory. Now, these are different terms from R and S, which also mean kind of right and left. Okay. So the R to butanol is actually also could be called L. Okay. So you could also call this. I'll write an L like this. L to butanol. That's an alternative stereochemical descriptor. And this would be what? D butanol. The R denotes the configuration of the chiral carbon. The D or L denotes how it rotates PP light. Please note, R and L has nothing to do with each other. Please don't think that R is always L. These two have nothing to do with each other. R and S is determined on the board by looking at the configuration. D and L you cannot tell from structure. D and L comes from experiment. Sometimes R may be L, sometimes R may be D. They have nothing to do with each other. But they both can be used as descriptors once we know that this is L. You don't have to know anything about the compound to know it's R. You can just tell that from drawing on the board. This is a physical data, that's an experimental observation. This is not an experimental observation, it's a on the board descriptor. Okay, so this is the idea of optical activity. This compound will rotate pp light. This compound will rotate in equal and opposite. It's because it's chiral. If the compound was not chiral, it would not rotate to pp light. A compound that does not rotate pp light is said to be optically inactive. It's not. Okay. We'll do more about optically active on the next page. A little practice at the top. Identify any chiral carbons. How about this guy? Any chiral carbons? No. All these carbons have two H's. Does that carbon there have 4 different things attached? No, it has a chlorine, an H. This and this is the same, because if you come this pathway, it's the same all the way around until you meet, and there's no difference. So this is like the same constituent coming off of that carbon. There's no chiral carbon here. No chiral carbon. Thus, are these enantiomers? Are these enantiomers? No, these are the same thing. Same thing. Why are they the same?
Because when you name it, you have to start from.
Well, in both cases, it's one chlorocyclohexane. But do they require different stereochemical descriptors? No. The carbon is not chiral. What does that mean? A chiral carbon is a point of asymmetry. Okay? Because that carbon is chiral, that means that there's no symmetry through that carbon. I mean, that's an H in 3 different groups. You cannot cut right through it and have the same. If I cut right through here, I've got green on one side, blue on the other. If I cut right through here, I got half a blue on one side, half a blue on the other, but I got green on one side, black on the other. A chiral carbon is a point of asymmetry. There's no symmetry there. But if the compound's not chiral, for example, if I have 2 of the same things on there, now we say, hey, that carbon is not chiral. What does that mean? That means it's no longer a point of asymmetry, that means it's symmetry. And if you have symmetry, now you can cut right through it and you have blue on one side, blue on the other. That's a symmetrical carbon. It's not chiral. Since it's symmetrical, you can cut right through it. I mean, if you built this compound, you can cut right through the whole thing. It has a plane of symmetry. And if a compound has a plane of symmetry, it's not chiral. Like, where's Waldo? We'll be doing that later. This is the same thing. These are the same exact compounds. Yes, if you just take it and flip it over, then the chlorine will be pointing forward. This is like drawing this hand on the board and then drawing it like this on the board and saying it's the same or different. It's the same. It's the right hand. Okay. That's why whenever the carbon is not chiral, usually most people don't even show the dash in the board. Yes, it's tetrahedral. But draw it however you want. As long as you have it connected, there's only one way to, there's only one projection. There's not 2 different projections. draw it however you want. Usually people just don't even draw it. But it is tetrahedral. Okay, over here, is there any carbons here? Is that carbon-carbon? What's the hybridization of that carbon? sp2, trigonoplanar. A planar carbon is not chiral. A planar object, as long as it's symmetrical, that's what atoms are, has a plane of symmetry. Something has a plane, like this notepad. Here's the plane. Okay, it could be as long all the way to the clock. It's planar. Just like that carbon is planar. The things around it are projected planar. Okay? Well, it has a plane of symmetry. You can cut right through this and have the same on both sides. Here, let's slice right through it. Boom. These are the same as long as they're the same thickness, etc. Okay? So they have a plane of symmetry. What about my hand? There's a plane. Well, the hand you actually cannot. If I cut right through, I'll have a top knuckle on one side and a palm on the other. Okay, so while it's planar, you can't do this. But see, atoms aren't like that. Atoms don't have knuckles on one side and palm on the other. Atoms are the same on both sides of the plane. Again, it's not tetrahedral. It's not chiral because to be chiral, it has to be a tetrahedral carbon. There's no chiral carbon here. Also, you would never show this like dashed or bold anyway because that's planar. It's all on the plane of the board. How many chiral carbons here? 1 chiral carbon. We've got a chlorine, an H. If you come this way, it's different from coming this way. So that's a chiral carbon. Because it's chiral, you can show that 2 different ways. So there's an R and an S form. R and S configuration at that carbon. You could draw them both. You would just draw one bold, one dash, and then you can determine it. Questions about any of that? You know, a huge part of learning a new topic is the nuances. You know, I could tell you just, hey, this is it, and give you like 5% and say, okay, 5%. But if you really want to understand it, there's 95 more %, and that takes covering like a million miscellaneous things. Well, you can either decide, do you want to try to talk about the miscellaneous things, or do you just want to say, okay, let's keep it very simple, and hey, let's identify chiral carbons, and let's move on. But if you really want to understand this stuff, you got to be thinking, you got to ask questions, and you got to realize that in class is very limited. All right, this is very limited part of the whole course is right here. Majority of the course is your outside time, forming your questions, and then boom, class time. More on optical activity. Okay. This is what we'll be doing in lab this week. Okay. How do you determine, okay, what if this liquid was chiral? First off, how would we know if this liquid was chiral or not? You have to shoot. Can you see the molecules? You can't see the molecules, right? You gotta remember that. You know, we can see molecules on the board, but what if I brought an unknown liquid here and said, hey, is this liquid chiral or not? How would you determine? I mean, what if you didn't even know the structure? I can't draw anything on the board. Could you tell if it was chiral or not? What experiment might you do? Shine light to it? Why? PP light? Because you know that if it's chiral, you know that a chiral molecule will rotate PP light, and a non-chiral one will not. So let's shine some PP light on it and see if it rotates it. That would be an experiment we could then test. You can't look at the molecules and tell. So you put it in some PP light. What is that, a polarimeter? Okay. Well, what if it doesn't rotate pp light? Does that mean it's not chiral? Well, hold on. Only the individual enantiomers rotate pp light. What if the molecule is chiral, but it's a mixture of both the R and S forms? Will that rotate pp light? Actually, it will not. Okay? Number one, a 50-50 mix of enantiomers gives no net rotation of pp light. By the way, what do we call a 50-50 mix of enantiomers? Put it in our notes many times before, I think. Racemic. Yes, a 50-50 mix of enantiomers is called racemic, a racemic mixture. And a racemic mixture does not rotate pp light. Just like a chiral molecule does not rotate pp light. This mixture doesn't rotate pp light net. What happens is half of it rotates one way, but the other half rotates just the opposite right back to zero. And so these cancel out and you get no net rotation. So if I ran the polarimetry of this and got no net rotation, first off we would say it's not optically active. That means it didn't do anything. But does that mean that my molecules are not chiral? Not necessarily. It's either an achiral molecule or I got a 50-50 mix of chiral molecules. Okay? Now, 50-50 mix is easy. It's zero rotation. What if it's 100% one enantiomer and 0% the other? Well, then it would rotate the maximum. That's like what we put on the board. If this was all R2-butanol, which way would it rotate? Let's look at 2-butanol. We put the numbers up. If this was all the R enantiomer, which way would it rotate?
Left.
Was R D?
R was L.
I'm sorry, no. I got to keep it right. Levo is left. R is right, because R is right. Levo is left. S is clockwise left. Okay. So R was D. Okay.
No,
so
R was L.
L is left. Levo, that's left. Okay. R was L. Okay. So R was negative 13.5.
Yeah.
R was L, negative. Okay. So if this was all R, it would rotate negative 13.5. If it was a 50-50 mix of R and S, it would rotate 0. That would be racemic. Question is, what if it's some type of ratio in between 50-50 and 100-0? What would that rotate? Okay, first before we do that, let's introduce the term enantiomeric excess. This is a common method for describing the amount of enantiomers in a mixture when it is not racemic, when it's not 50-50. Now, what is this? The enantiomeric excess is the excess of one enantiomer that exists beyond racemic. Now, once you understand it, that statement explains what it is. What is that statement? The excess beyond racemic. Let me try to explain. Thus, a mixture that has an EE of 10% R has a composition of 55% R, 45% S. You've got to understand where these two come from. It might be easier to go the other way first. If this was your ratio, the EE is 10%. This is the way I present it. If 45 of S and canceled 45% of R. Okay? Those are going to cancel each other. That would be your racemic. If this cancels 45% of R, how much of R are you left with? 10%. 10% is the excess beyond racemic. These cancel, you're left with 10% that was not canceled. That's the EE. Now, some students look at EE of 10% R and say, hey, I've got, I don't know, 90%, 10%? No, that's not what this means. Let's try a problem here. What is the ratio of D to L isomers in a mixture that has an EE of 60% D? Somebody says 80-20. 80-20 with which one's D? EE of 60% D. It's an excess, an enantiomeric excess of D. That means there's more D. So this is D to L. Yes, a 60% EE means you have an 80-20 ratio. Because 20 of this cancels 20 of that, right? If we can convert this to 60 and 20. 20 cancels 20. What are you left with? 60 of D. That's why it's called a 60% EE. Okay? Let's go the other way. What is the EE of a sample that is 70-30 DL? That is 70% D and 30% L. What's the EE? 40% D. Yeah. EE equals 40% D. Basically, 30% of this, we can turn this into 40 and 30. 30 cancels 30, and you're left with 40%. 40% is the excess that's left after racemic. Now, I tried to just explain it to you. If you want an equation to work, look in the book. Okay? I don't know what the equation is. I hopefully tried to explain how you do it without having to rely on just putting in some numbers in a mundane equation, which you never understand in your 4 years of college. Understand it. Once you understand it, nobody can remove that understanding. It's yours. We did both of those? Okay, that's EE. And so EE is how you commonly quote the composition, basically. How do you determine EEs? We do this by polarimetry, shining the light. Okay, we got to understand that only the excess beyond racemic will rotate DP light. And actually, the percent rotation is the same as the EE. Thus, a mixture with a ratio of 80-20 R to S, which, by the way, is a 60% EE, will rotate PP light 60% of max. Okay? The maximum rotation is the same as the EE. Why? Well, this is 80%, 20%, right? 80-20. 20 cancels 20, so we can turn this into 60-20. In terms of rotation, this rotation will cancel that rotation. Because 20 goes this way, the other 20 goes the opposite. These cancel, what are you left with? That's what gives you your net rotation. But this is going to be 60% of max. Because it's not 100% that rotate, only 60% rotate. So it's the same as the EE. Let's do a problem. What would be the degree of optical activity? Another way to say it is, what's the specific rotation of a 60-40 RS mixture of 2-butanol? First off, what's the max of 2-butanol? Plus minus what? That's the max, right? But you only get that if it's 100% one or the other. What if it's a 60-40 mix? Well, 40 cancels 40. What are you left with? These cancel, you're left with 20. 20 of which one? 20 of R. So you only get 20% of the rotation. What's 20% of this? 1.35 times 2, 2.7. Okay. 2.7. Is it going to be positive or negative? R. I can't remember what R was. Oh yeah, R was L, which is negative. A 60-40 mix would give that rotation. Now, if you were doing the experiment, you would start by determining this number. Then you would work backwards and get to that ratio. How do you work backwards? I think the next question works backwards. A here. I think this goes the other way. But this is what you'll be doing in lab, because again, maybe I got a mixture of enantiomers. First thing you do is you would determine the rotation. So let's determine the rotation, and it comes out to be this. But we know the max is plus or minus 13.5 because we're still doing 2-butanol. Well, this ain't 13.5, so this must not be a pure enantiomer. It must be a mixture. We also know the mixture is not 50-50, because if the mixture is 50-50, this would be what? 0. Now, since it's negative, that means we have more of which one in the mixture? R, because R is the one that goes negative. So there's more of the negative. But what's the ratio? Well, how do we do this? We're going backwards from what we did above. Max is 13.5. What percent is this of max? This is what percent of max? Is it 75%? Probably some whole number, because that's why I gave 10.13. Now, I don't know the math to get 75%. I haven't had math in a long time. But somehow you got to say this is what percent of max, and the answer is 75%. Now that you know it's 75% of max, thus the EE equals 75% of R, because it's negative. But that's not the question. What is the ratio? If it's 75% E, what's the ratio? Vlad, did you have it? What's the ratio of the two? If this is the EE. Tara, you have it?
87.5 and 12.5.
Yes, 87.5 R, 12.5 S. There's your ratio. How did you get that? Well, ultimately we know that we have to have something with 12.5 cancels 12.5 of that. What are we left with? We're left with 75% R. Does everybody see how we got 87.5? Questions? If you want some math formula, you can look in the book, but I just did it. Okay, we'll be doing that in lab this week because you'll be determining this number here. We'll take the naproxen sodium, we'll dissolve it. Okay, it's then put in a polarimetry tube, and you put the tube in a polarimeter and you try to determine a number. First off, it won't be this number because this is a specific rotation. That's been normalized. And you'll learn what that is in lab. Okay? The number you get from the instrument first has to be manipulated mathematically to get to this, because this is based on concentration. Then when you get that, you can do your math to determine this. Now, since one enantiomer is toxic, hopefully it's 100 to 0. We'll see if we get it.
What's the instrument that ever?
Do what?
What's the instrument that ever?
That's a good question. Yeah. What kind of instrument quality do you have? It's always a good question. In fact, if I was on the witness stand and I just presented the data, that'd be a good question there under cross-examination. Excuse me, sir, can you discuss your instrument, your instrument quality? What kind of instrument are you using over there at? Is that instrument in service any longer? Is that the same instrument that in 1989 was known to be defective? How are you, okay? Okay, something to be working on. Fisher projection, spelled with a C. Fisher projection. This is the same Fisher that did all other types of stuff. Fisher projections. This is similar to Newman projections. It's a way to show the stereochemistry on the board or on your paper. Let's show Fisher projections of this compound. This should be this compound here, S. Okay. A Fisher projection is, we show the chiral carbon as a crosshair. But we don't show any dashed or bold. It's implied. When we see a crosshair, I'll draw the carbon in. The things at top and bottom are implied to be going back. And the things on the side are implied to be coming forward. Okay? So whenever you see the crosshair, that's what it implies. Things on the side are sometimes like a bow tie, or maybe they're trying to hug you or something, but things on the side's coming out. Okay? Now here's our chiral carbon, and it has 4 different things attached. Maybe we should draw this, have this molecule here. Black straight up for methyl H here, chlorine green, coming towards you guys, bromine blue going back. So here's the molecule. Okay? Now I'm looking at it. We want to draw it with, I'm looking at it, the thing's going, I got something going up and down but back. For example, let me just go over here. Not like that. The things on the side are coming towards you. See how they're coming towards you? The thing going up is going a little bit back. So that's sort of like on the board like this. That's how we're kind of drawing it. Okay. Now, remember how we stood on the side with the Newman projections? We do that here. We're going to stand over here with our feet on the ground, and we're going to look through here. I'm looking at that carbon right there. Now on that carbon, I see something going straight up. What's going straight up? The methyl going straight up. Okay? There's the methyl. It's going straight up. Now, looking at this carbon, something going straight down towards the ground. What is that? H. Okay? On this carbon, something's coming towards you guys.
Chlorine.
And if I'm over here looking at the carbon, what's coming towards you guys? Chlorine. So that's on my
Right.
right. Now here's the carbon. What's going behind the board, which is, if I'm over here, is on my left? Bromine. Okay? So there's that compound in a Fisher projection. Let's look at like this again. Methyl going up. H here. Chlorine, bromine. Now, I'm going to turn this a little bit like this, so that's going up and back. The H is going down and back. There it is on the board. I just drew what I see, but when I drew it here. So this is over here, turn. There it is on the board. Alpha going up, but back, right? Does it not mean back? Here's the H, it's down, but it's also going back. Chlorine's over here, but it's coming forward. Bromine's over here, but it's also coming forward. So there it is on the board. Now, is this really S, or am I lying to you? Is this really S, or am I lying to you? Is this the S configuration? What's high priority group on the carbon? Bromine, what's next?
Chlorine.
What's next?
Methyl.
Carbon. Okay. R or S? Is the low priority group back? No, it's not back. Bromine's back. Is it low? Okay. Because if it was back, we could just say 1, 2, 3. It's S. You would get the right answer only by low. Is the low priority group forward? No. If it was forward, we know that we can just reverse our mind. The low priority group is in the plane, so how do you deal with it? Well, you have to either rotate the molecule or your view. But we've already rotated the view. That's the power of the Fisher projection. Let's do RS here. 1, 2, 3. Now, is the H forward or back? It's back because that's what this means. We've already done that work. Since it's back, 1, 2, 3 is counterclockwise. What's the answer? S. I was not lying to you. It's S. What I just showed you is an example of when the low priority group is in the plane. That takes a little more work. Now you can envision, okay, if I'm over here and the H is going away from me. And you can say, hey, I got bromine at 9 o'clock, chlorine at 3, and I can see it's S. But I'm doing a lot of thinking in my head. Put in a Fisher projection, then you can help determine RS. Okay. What do we have over here? Next, show the R enantiomer in a Fisher projection. Show this one in a Fisher projection. Now, you can cheat here a little bit because once we do one, then you know the other one is. If this is R, isn't it the mirror image? Well, you can just say, hey, I know it's the mirror image, so I'm going to draw the Fisher. That. Are these two mirroring each other? Yeah. If they are, then the configuration is R. That's a little bit cheating though, because we really didn't, we just relied on what we did over here. Another way to do it is to say, okay, let's stand here. Look through here, because I want to look at it with one group going up and down, methyl going up, H going down and back. If I'm looking through here, the chlorine is on my left, and the bromine is on my right. Chlorine's on my left, bromine's on my right. I could have drawn it also. Okay, when's the lab report due? The lab report is not due in lab because the topic that we need to cover lab report is D, compounds with more than one chiral carbon. We'll have to see how far we get. Right now I'm going to say the lab report is due on Monday here in class for both labs. Bromination lab report Monday here in class. Okay? We'll see if that's going to be good on Friday, but I think it will be. Bromination lab report Monday here in class. Let's look at compounds with more than one chiral carbon. Example here. How many chiral carbons do you see? I see 2 tetrahedral carbons with more than 4 things attached. Okay? How many stereoisomers are possible from the following compound? How many stereoisomers possible for 2-butanol? If that wasn't there, it'd be 2-butanol. How many stereoisomers possible for 2-butanol? 2. So R and the S form. Okay? How many stereoisomers are possible for this compound? 4. How did you get 4?
2 per chiral carbon.
Yeah, can you imagine? Can we draw 4? 4 is the answer. Let's draw them. Let's remember this for Friday because I want to have the backbone to say. We can show the OH bolded, and we can show the chlorine bolded. How about that? Can you show 3 other ways? How about, let's keep the backbone the same. How about this bolded and this dashed? This dash. And this what? This could be either dashed. And then real quick, the fourth one. And then let's see what we can handle. What is this one got to be? Dashed and oh. Okay, here are 4. Please do R and S for each of these. Okay. Once you do one, you can kind of cheat on the others. What formula did we use here? How did you get 4? We need to have. There's a formula that's worth using. Please pick up here. What's the relationship between these? Can you draw these in a Fisher projection? And what's a diastereomer? We'll pick up here on Friday. Have a good day, guys. We'll meet in lab downstairs. Tomorrow and Friday.